In an industrial facility, you can find a number of different ways in which power is supplied to devices so that they can do work. For example, the power may be supplied by electric motors, like this one here. Or it may be supplied by internal combustion engines, like this diesel engine. Another way to provide power to do work is with a hydraulic system. Basically, a hydraulic system is a group of components that work together to transmit power by applying a force to a confined liquid. Hydraulic systems are often used in situations that require a great deal of force to move an object or device, such as positioning large valves like this one. And in this example, a hydraulic system is used to raise, lower, and support an extremely heavy object. Hydraulic systems can also be used to operate rotating equipment, like the belts on this machine. In this program, we'll discuss some principles of hydraulic power and look at how a system operates. We'll also take a look at what operators can do to help make sure hydraulic systems work properly. Before we get into the nuts and bolts of hydraulic systems, let's talk about some basic principles to help you understand how they work. Earlier, I mentioned that a hydraulic system transmits power by applying a force to a confined liquid. The way this works is based on principles associated with pressure and flow. One of these principles, called Pascal's law, simply put, states that pressure applied on a confined fluid is transmitted in all directions and acts with equal force throughout the fluid. Let's look at an illustration to see the role that Pascal's law and other principles play in making hydraulic systems work. This illustration includes two containers with hydraulic fluid. The containers are connected by a line that provides a flow path between them. One container is wider than the other. We'll see why a little later. This container has a piston inside, and this one is sealed at the top, confining the fluid inside. Now, let's apply a force to the piston. Since liquids are generally considered to be non-compressible, that is, their volume remains the same when a force is applied, the fluid in the container resists the force. As a result, the force creates pressure on the fluid, which is transmitted throughout the container. The amount of pressure that's transmitted throughout the container is equal to the applied force divided by the surface area on which the force is exerted. If the force is measured in pounds and the surface area is measured in square inches, the resulting pressure is expressed as pounds per square inch, or PSI. For example, let's say that the amount of force applied to the piston is 5 pounds, and the piston has a surface area of 1 square inch. This results in a pressure of 5 psi, which is transmitted throughout the container. Now, let's remove this piston, seal the container, and place a piston on this side. As pointed out earlier, this container is wider than the other one. We can place a piston inside it that has a larger surface area than the piston we removed from the other side. Let's say its surface area is 10 square inches. Now, let's see what happens when we apply a 50-pound force to it. Since pressure is equal to the force, 50 pounds, divided by the surface area, 10 square inches, on which the force is applied, this amounts to 5 psi throughout the containers. So, even though a much larger force was applied to this piston, because the piston's surface area is much larger, the resulting pressure is the same as that created on the other side. This means that the 5 psi created by the force on the smaller piston can balance a 50-pound force, or load, applied to the larger piston. By producing a force greater than the force applied to the fluid, a mechanical advantage is created that's 10 times greater than the 5 pounds of force applied to the smaller piston. Now, actual hydraulic systems are not just designed to create a mechanical advantage. They're designed to cause movement as well. Let's see how. Right now, 5 pounds of force on the smaller piston creates just enough pressure in the fluid to support the 50-pound load on the larger piston. To overcome the force on the larger piston and cause it to move, a greater force has to be applied to the smaller piston. So, let's apply 6 pounds of force. The added force on the smaller piston increases the pressure of the fluid great enough to overcome the force on the larger piston. This causes the fluid to flow into the other container, pushing the piston upward. Notice that the small piston moved much farther than the larger piston. The distance that the larger piston moved basically depends on 2 factors: the volume of fluid displaced by the movement of the small piston and the surface area of the larger piston. The first factor can be determined by multiplying the surface area of the piston by the distance the piston moves. Let's assume that the small piston moved 10 inches. Since we already know that the small piston has a surface area of 1 square inch, then the volume of fluid displaced by its movement is equal to 10 cubic inches. Now, as the 10 cubic inches of fluid was displaced, it moved into this area. Now, this is where the second factor comes into play. Since this area is much larger than the area with the small piston, the 10 cubic inches of fluid didn't move this piston as far as the small piston moved. The actual distance the larger piston moved can be determined by dividing the displaced volume of fluid by the surface area of the piston. We know that the volume of liquid is 10 cubic inches, and the surface area of the large piston is 10 square inches. This amounts to 1 inch of movement. So, in this example, a 6-pound force is applied to the small piston, moving it 10 inches, which results in moving a 50-pound force on the larger piston 1 inch. This illustrates the basic concept by which hydraulic systems operate, using a small force to move a much larger force. What we've seen so far helps explain how a hydraulic system is able to transmit power or energy through a liquid in order to do work. But this illustration represents only a few components of an actual hydraulic system. For instance, the mechanical force that pushes on the fluid in a system is provided by a pump, such as this one. The fluid is carried throughout the system in lines to the component that moves an object or device. In an actual system, this component is called an actuator. There's still other components used in hydraulic systems. When we return, we'll take a closer look at some of them and see how they work together. In the meantime, read the material we've covered in your text and answer the questions at the end of the section. Earlier, we looked at some basic principles of hydraulics that apply to the operation of a hydraulic system. But to understand how an actual hydraulic system works, you need to be familiar with the components that make up the system. So, in this part of the program, we'll take a look at the function of components in a typical hydraulic system, and we'll see how a system operates. Later, we'll take a closer look at the operation of some of these components. As you know, the job of a hydraulic system is to move a large force with a smaller one by pushing a volume of fluid through lines. In hydraulic systems, the supply of fluid is stored in a tank called a reservoir, like this one. Its main purpose is to store the fluid until it's needed by the system. The smaller force that's applied to the fluid is provided by a pump. In this system, the large force that has to be overcome is a very heavy object, which is raised and lowered with this component, called an actuator. This one is an example of a linear actuator, which means that it produces movement in a straight line. Now, these are different types of devices that also use fluid power to operate equipment. They're called hydraulic motors. However, hydraulic motors produce rotary movement. These particular ones are used to turn the belts on this machine. Now, to rotate, raise, or lower a load, a way of controlling the direction of a hydraulic motor and actuator movement is often needed. This is usually done with a directional control valve. In many cases, it's also important to control how fast the load is moved, so a flow control valve, such as this one, may be used. Finally, since many hydraulic systems can be damaged if fluid pressure gets too high, some kind of pressure control valve, like this relief valve, is often used to prevent overpressurization. Now, we've seen some major hydraulic system components and the basic role they play in system operation. We'll take a closer look at some of these components later in the program. But for now, let's get an idea of how these components work together and the way fluid flows through a system. This illustration of a hydraulic system includes a reservoir with hydraulic fluid, a motor-driven pump, fluid lines, a filter or strainer, valves, and an actuator. The actuator basically consists of a cylinder, a piston, and a piston rod. During operation, hydraulic fluid first passes through this strainer on the pump inlet line. The strainer traps small particles and prevents them from entering the pump, and damage continues through the line to the pump. The pump's basic function is to convert mechanical power into hydraulic power by applying force to the fluid and moving it through the system. The pressurized fluid leaving the pump passes through this pressure control valve, called a relief valve. When system pressure is normal, fluid flows from the valve to the other components in the system. As mentioned earlier, the relief valve helps prevent system overpressurization. If system pressure exceeds the preset maximum, the valve will open and route excess fluid back to the reservoir. But under normal system pressure, the fluid from the relief valve passes through another valve called a flow control valve. It's used to regulate fluid volume to and from the actuator, which controls how fast the actuator piston moves. Fluid leaves the flow control valve and goes to this directional valve. It controls the direction of fluid flow by routing it to either end of the actuator. In this example, the directional control valve routes the fluid to the lower end of the actuator. The fluid enters the cylinder, pushes against the piston, and moves it upward. The actuator in this example has fluid on both sides of the piston. So when the piston rises, the fluid above the piston is routed through the directional control valve and sent back to the reservoir through this line. To reverse the direction of the actuator piston, the directional control valve will route fluid flow to the upper end of the actuator, pushing the piston in the opposite direction. Fluid on this side of the piston is routed through the directional control valve back to the reservoir. Well, that's basically how fluid flows through a hydraulic system. At this point, we should have a pretty good idea of the function of components in a hydraulic system and how a system works. Keep in mind that the hydraulic system we've looked at is only an example, and the ones in your facility may look different and consist of different components depending on the purposes and needs of the system. However, the principles of operation are basically the same for most hydraulic systems. Take some time now and read your text to help you fully understand the material we just covered. As mentioned earlier, hydraulic systems use different types of valves to control fluid in a number of ways. We've already talked about the basic function of one type of pressure control valve, a relief valve, which prevents system overpressurization. In this part of the program, we'll take a closer look at the roles pressure control valves play in a hydraulic system, and we'll see how the valves work. As you know, a pump provides the flow of hydraulic fluid at a certain pressure throughout a system. Well, this pressure has to be maintained to help ensure efficient system operation. Excessive pressure in a system could cause flexible hoses or lines to rupture, or seals and other components to be damaged. A pressure control valve, such as this relief valve, is designed to prevent that from happening. Earlier, we saw where relief valves fit in a hydraulic system. If system pressure gets too high, the relief valve opens and diverts the excess fluid from the pump back to the reservoir. There are a variety of relief valves that can be used in a hydraulic system. This illustration shows a simple relief valve consisting of a body, a disc and valve stem to guide it, a seat, a spring, and an adjusting screw. The valve body provides a path for the fluid to flow and holds all of the other valve parts in their proper positions. When the system is at normal pressure, the disc rests on the seat and is held in place by spring tension, keeping the valve closed. The adjusting screw is used to vary the tension on the spring, allowing the valve to be set to open at any pressure within its specified range. Generally, a relief valve is set to open when the pressure in a system reaches a preset maximum safe pressure. If pressure in the system reaches the limit, the pressure on the disc begins to overcome the tension on the spring, and the disc begins to lift off of the seat. As this happens, the pressurized fluid is released through the valve outlet back to a reservoir. If the pressure in the system continues to rise, the disc will continue to lift until it has risen as far as it can go. As soon as system pressure begins to decrease, spring tension begins to push the disc back towards the seat, and when the pressure returns to below the maximum safe limit, the valve completely closes. While the relief valve we just looked at opens and diverts excess fluid to a reservoir when pressure gets too high, there are other types of pressure control valves that work differently and serve slightly different functions. For instance, a hydraulic system may be designed to provide fluid to certain parts of the system at less than the normal operating pressure. This is accomplished with pressure-reducing valves. Let's take a look at this simplified illustration of a pressure-reducing valve and see how it works. Its parts consist of an inlet, an outlet, and a pilot valve that consists of a disc, spring, adjusting screw, and a drain. There's also a hollow spool that includes a spring and an orifice at the bottom. The desired outlet pressure is set with the adjusting screw, which varies spring tension on the pilot valve disc. When supply pressure is less than the desired outlet pressure, fluid enters this inlet, flows around the spool, and leaves through the open outlet. Although fluid is present inside the spool and at the pilot valve disc, at this point, the pilot valve and spool have no impact on the valve operation. However, if the inlet pressure is greater than the desired outlet pressure, then the pilot valve and spool come into play. Since fluid pressure is sensed at the pilot valve disc through the hollow spool, the higher inlet pressure at the disc overcomes the force of the spring. The spring contracts and flow is diverted to the drain passage. At the same time, fluid flow through the orifice creates a pressure difference that causes the spool to move upwards. As the spool moves upward, it partially closes the outlet. This action, along with draining off a portion of the fluid through the pilot valve, effectively reduces the pressure of fluid leaving through the outlet to the other part of the system requiring lower operating pressure. Now, only enough fluid flows through the outlet to maintain the preset pressure. In this example, the outlet is never completely closed. When no flow is needed in the other part of the system, there is a small but continuous flow through the spool, the pilot valve, and to the drain. Well, that's basically the way this type of pressure control valve is used to reduce system pressure. Now, we've seen a couple of ways to control pressure in a hydraulic system, and you should have a basic idea of how pressure control valves can reduce system pressure when needed and how they prevent system overpressurization. When we return, we'll take a look at some valves that control fluid direction in a hydraulic system. In the meantime, read your text and make sure you understand the material we've covered so far. In this part of the program, we'll take a closer look at the function and operation of directional control valves, such as this one. It's used to control the direction of fluid flow in a hydraulic system. For example, a directional control valve is used to control the direction that an actuator moves the fork on this forklift. The directional control valve is operated manually by positioning a lever. When the lever is in one position, the fork can be raised. In another position, it can be held in place. And one more shift of the lever positions the valve so that the fork can be lowered. Now that we've seen what a manually operated directional control valve can do, let's see how one works. This illustration includes a directional control valve, an actuator, and fluid lines. The directional control valve consists of a valve body, a spool, springs, a lever, and fluid lines. Connected to this line is a fluid inlet passage through which hydraulic fluid is supplied at a constant pressure. There are also several fluid outlet passages. One fluid outlet passage is connected to the line on one side of the actuator cylinder, and another outlet passage is connected to the fluid line on the opposite end. And these two outlet passages are connected to a return line that allows fluid to return to a reservoir. The lever is used to move the spool, which is what controls the direction of fluid flow. So, let's look at the flow path through the valve with the lever and spool in different positions. Right now, the lever is in the center, or neutral position. With the help of the springs, the spool is held so that it blocks both outlet passages to the actuator. In this example, when the lever is moved in this direction, the spool is lowered. Hydraulic fluid is supplied through this line and enters this end of the actuator, pushing the piston. At the same time, fluid is vented from the top of the cylinder and flows through this outlet passage to a reservoir. The movement of the actuator is reversed when the lever is moved in the opposite direction. This action raises the spool, which blocks this outlet passage and opens this passage to the actuator. Hydraulic fluid is now supplied to the other end of the actuator, pushing the piston in the opposite direction. The fluid on this side of the piston is vented through the open outlet passage to a reservoir. When the spool is returned to the neutral position, the flow of fluid to and from the actuator is blocked. This traps the fluid on both sides of the piston, which holds the piston in place. Now, that's one way that a directional control valve works. Keep in mind that there are different ways to control fluid direction and different ways that a directional control valve can be operated. The one we just saw was operated manually. However, this is a directional control valve that works automatically. In response to an electrical signal, it routes flow to a hydraulic motor to cause the motor's drive shaft to turn in either a clockwise or counterclockwise direction. Here's a cutaway model of a directional control valve similar to the one we just saw. The valve is operated by solenoids. Let's look at an illustration to see how it works. It basically has the same parts as the manually operated directional control valve, but instead of using a lever, it uses solenoids that respond to electrical signals from a control system to position the valve spool. The solenoids basically consist of wire coils and springs. In this example, one solenoid is attached to the top of the spool, and one is attached to the bottom of the spool. When this solenoid is energized, a magnetic field is created around the coil. The spool is attracted to the magnetic field, which pulls the spool downward and compresses the spring. With the spool in this position, fluid is directed to the bottom of the actuator, pushing the piston upward. And fluid on the other side of the piston is vented to the reservoir. When it's de-energized, the spring expands and forces the spool back into its original or neutral position. This blocks the flow to and from the actuator, and the piston is held in place. The same thing happens when the other solenoid is energized and de-energized, except that in this case, the spool moves in the opposite direction. So, when the solenoid is energized, fluid flows to the opposite end of the actuator, causing the piston to retract. And the fluid below the piston is vented to the reservoir. When the solenoid is de-energized, fluid flow is blocked and the piston is held in place. Now, that's basically how one type of solenoid-operated valve works. Since there are a variety of directional control valves used in hydraulic systems, the ones used in your systems may not look and work exactly like the ones we've seen here. But you should have a basic idea of how these control valves perform their function. Well, so far we've looked at some ways in which fluid direction and pressure are controlled in a hydraulic system. When we return, we'll take a look at some ways that flow is controlled. But before we do, take some time and read your text. Make sure you understand the material we've covered and answer the questions. So far, we've seen some ways that fluid pressure and direction are controlled in hydraulic systems. Well, in addition to controlling fluid pressure and direction, in many systems it's also important to control fluid flow. That's the function of flow control valves. By controlling fluid flow, a flow control valve, like this one, can regulate how fast an actuator moves. For example, it may be necessary to operate an emergency system valve relatively quickly. On the other hand, a heavy load like this one may have to be moved quite slowly. Depending on the purposes of a hydraulic system, flow control valves may be used to control the flow of fluid to an actuator or from an actuator. We'll look at some different methods of accomplishing these tasks and why they're necessary. Then we'll take a look at how a flow control valve works. Three basic methods we'll discuss include meter in, meter out, and bleed off. The first method we'll talk about is meter in. With the meter in method, the flow control valve is used to control flow going to the actuator. Let's use this simplified illustration to see how. Here we have an actuator with fluid lines, a directional control valve, and a flow control valve. The flow control valve is placed in the supply line before the directional control valve so that the flow of fluid supplied to either side of the actuator can be controlled. With this arrangement, fluid flows through the supply line to the flow control valve, which then measures or meters the proper volume of fluid into the directional control valve. In this case, the directional control valve routes the measured amount of fluid to the lower end of the actuator, causing the piston to travel through the cylinder at a constant speed. Because in this example, the directional control valve is located between the flow control valve and actuator, flow to the opposite end of the actuator also can be metered in. This allows controlled movement of the actuator in the opposite direction. The fluid returning from the actuator is controlled only by the movement of the actuator. Because of that, a heavy load that exerts a force in the same direction as actuator movement could cause the piston to move at an uncontrolled speed. This would cause the load on the actuator to run away. So the meter-in method is suited for applications such as operating this valve. The valve can be opened and closed gradually and smoothly, but it doesn't exert enough force on the actuator to run away. In situations where runaway may be a problem, a different method, like meter out, is typically used. This is an example of the meter out control method. As its name implies, it's used to control the flow of fluid returning from the actuator. It's located in the fluid return line between the directional control valve and a reservoir. This allows the speed of the actuator to be regulated by controlling fluid flow returning from the actuator. When fluid flows into the lower end of the actuator, the fluid on the opposite side of the piston is exhausted through this line to the directional control valve. The directional control valve routes the fluid to the flow control valve, where the fluid is metered out of the valve and sent to a reservoir. In this way, the flow control valve determines how fast the piston and rod extends. When fluid flows to the upper end of the actuator, the action is reversed. Now the speed at which the piston retracts is controlled. So with a meter out arrangement, not only is the lifting of a heavy load controlled, lowering the load is also controlled so that it can't run away. The third method of flow control we'll talk about is bleed off. With this method, the flow control valve is placed in a branch line off of the fluid supply line before the directional control valve and the actuator. With this method, a metered portion of the fluid to the directional control valve is bled off to a reservoir. This method is similar to meter in, except that the measured flow is to a reservoir instead of to the actuator. Bleed-off flow control is useful where a system supplies more than one actuator operating at different speeds. Whether a hydraulic system in your facility uses a meter-in, meter-out, or bleed-off method of flow control largely depends on the system's application. And in some cases, all of these methods may be used together in the same system. The type of flow control valve used also depends on a system's purpose. To get an idea of how a flow control valve is designed and works, we'll take a look at a simplified illustration of one type. The parts of this flow control valve include a throttle, a spring, a spool, and a fluid inlet and outlet. In this valve, the spool is normally in the open position. Fluid enters the valve through the inlet, flows through the throttle, and passes through the outlet to an actuator. Fluid pressure is sensed in the chambers below and above the spool. The actual flow control is accomplished by the throttle. The throttle is simply a cylindrical-shaped piece of material with a notch cut into it, which reduces the area through which the fluid must pass. The throttle can be adjusted to provide the proper flow rate through the valve. This device is also pressure compensated, meaning that it automatically adjusts for changes in fluid pressure. This is accomplished by the spool. The spool senses workload pressure above it and fluid supply pressure below it so that a constant differential pressure is maintained across the throttle, thereby ensuring constant flow. Basically, in response to changes in inlet and outlet pressure, the spool can move up to close the inlet, or the spool moves down to open the inlet. This allows only that amount of fluid to enter the valve that can be forced through the throttle. Keep in mind that some flow control valves are better suited for certain applications than others. So the type of valves used in your systems may depend on factors such as whether a meter-in, meter-out, or bleed-off method is used. But regardless of the flow control method or type of valve, the main purpose of controlling flow is to regulate actuator speed. When we return, we'll take a closer look at the parts and operation of actuators. For now, though, take a break so that you can read your text and answer the questions. Earlier, we saw how various control valves are used to control fluid in a hydraulic system. The purpose of all this fluid control is to properly help transmit power to the components in the system that do the work. Those components are usually linear actuators, such as this one, or hydraulic motors, like the one here. As you may recall, the function of hydraulic actuators and motors is to move a load or device. Being familiar with the operation of these components can help you be more effective in keeping a system operating properly and dealing with problems that may arise. So, in this part of the program, we'll take a closer look at hydraulic actuators and motors to see their major parts and how they work. Hydraulic actuators produce linear motion, like the piston and cylinder we saw earlier. On the other hand, hydraulic motors, like this one, produce rotary or circular motion. We'll begin with a closer look at two types of linear hydraulic actuators, the single-acting and double-acting types. This particular actuator is a single-acting one. In this actuator, fluid flow acts on only one side of the piston to raise and support a heavy load. When the fluid is allowed to flow back out of the actuator, the weight of the load supplies enough pressure to return the piston. Let's take a look at this illustration to get a better view of how this kind of single-acting actuator works. The main parts of this actuator include a cylinder, a fluid port, a vent, a piston ring, and a piston rod. The cylinder is a hollow, rigid metal tube through which the piston moves. The fluid port is an opening in the cylinder that allows fluid to enter and exit. The piston ring forms a seal that prevents fluid from leaking between the piston and the cylinder wall. When the pressure of the fluid is greater than the force of the load, it flows into the port and moves the piston upward. This, in turn, moves a device or load that's normally attached to the end of the piston rod. The area on the other side of the piston is vented to atmosphere to prevent air from being trapped and compressed, which could restrict the movement of the actuator. When the flow of fluid stops, the piston and piston rods stop and are held in their new position by the fluid trapped under the piston. When fluid is allowed to flow back out of the actuator, the weight of the load causes the piston to move downward. In some single-acting actuators, the piston may be assisted in returning to its original position by using a spring in the cylinder. When fluid flows into the cylinder, the piston rises and compresses the spring. And when the fluid is allowed to flow out of the cylinder, the spring expands and helps force the piston back down. We've just seen how fluid flows only to one side of a piston in a single-acting actuator. On the other hand, in a double-acting actuator, fluid flow can be applied to either side of the piston. This is the type we've seen earlier. Let's take a look at this double-acting hydraulic actuator to get a closer look at how this works. Its main parts are nearly the same as the single-acting one. The differences are that the cylinder on this double-acting actuator doesn't have a vent, and it has two fluid ports instead of one. The two ports allow fluid to enter and exit on both sides of the piston. Fluid can enter this port to move the piston up, and it can enter this port to move the piston down. When fluid enters the lower port, fluid flow pushes the piston and piston rod upward. At the same time, an equal volume of fluid flows out through the upper port. The piston stops when the flow of fluid through the lower port is stopped. Fluid is then trapped on both sides of the piston, effectively locking it in place. To return the piston, fluid is supplied through the upper port, causing the piston and piston rod to move in the opposite direction. When this happens, an equal volume of fluid flows out of the lower port. The flow of fluid entering the cylinder and bled from the cylinder is controlled by a directional control valve. Now that we've seen how linear movement is produced in actuators, we're ready to find out how a hydraulic motor produces rotary motion. This is a small model of a hydraulic motor's inner parts. I'll remove this plate so we can get a better look at them. This part is called a cylinder. It has a somewhat elliptical shape and houses a rotor which is perfectly round. When the motor is in operation, the rotor turns inside the stationary cylinder. These rectangular vanes can slide in and out of slots on the rotor. When the vanes slide out of their slots, they follow the surface of the cylinder, forming sealed chambers that carry fluid around the cylinder as the rotor turns. As the rotor reaches a certain point in the cylinder, the vanes are forced back into their slots and the fluid is discharged. Normally, one end of a drive shaft is attached right here to the rotor, and the other end can be connected to a load. Now let's use a simplified illustration to see how a hydraulic motor works in operation. This hydraulic motor includes the same parts we saw on the model. It has a cylinder, a rotor, and vanes. These are fluid inlets, which are located 180 degrees apart, as are the fluid outlets. During operation, fluid is pumped through the inlets and into the chambers between the extended vanes. The fluid pushes against the vanes, causing the rotor to turn. Then, as the vanes pass the outlets, the chambers line up with them. The vanes are forced back into their slots, and the fluid is forced out through the outlets and returned to a reservoir. The turning rotor can also turn a drive shaft, which then can turn a device. The operating speed of the motor can be controlled by the flow rate of fluid supplied to it. Generally, springs are used in hydraulic motors to keep the vanes extended against the cylinder wall during operation. The fluid flow to a hydraulic motor can be reversed to cause the rotor to turn in the opposite direction. This makes it possible to reverse the turning direction of the device connected to the drive shaft. In a hydraulic motor, just as in a double-acting piston actuator, flow can be reversed with the use of a directional control valve. Now, that's basically how a hydraulic motor produces rotary motion. By now, you should have a good idea of what makes a hydraulic system work. But in order for a system to accomplish its job effectively and efficiently, it has to work properly. When we return, we'll take a look at some things you can do to keep them working the way they should. For now, though, read the material we've covered on hydraulic actuators and motors in your text and answer the questions. As long as the components in a hydraulic system function properly, the system can effectively provide power to operate a device or move a load. Undetected problems with any one of the components can result in faulty system operation, damage to other system parts, or system shutdown. Part of an operator's job is to identify potential problems before they get out of hand and take the appropriate corrective action. This can be accomplished by regularly inspecting a hydraulic system. In this part of the program, we'll look at some typical checks that operators should make on hydraulic systems to keep them working the way they should. One part of an operator's job in checking any system involves looking for obvious signs of damage. In this case, looking over the fluid lines for leaks, especially around connections, is also important. If a leak is found, any accumulation of fluid on the floor is slippery and should be cleaned up to avoid causing falls. Then, the appropriate action should be taken to have the leak repaired. If hydraulic fluid has been added to a reservoir more than usual, it's a good indication that there's a leak somewhere in the system. In addition to concerns about fluid loss, operators also need to pay attention to the fluid's condition. It's important to keep the fluid clean and moisture-free to help it last longer and avoid contamination damage to components in a system. One step that operators may have to take to help ensure fluid quality is sampling. The bottom of this reservoir has a valve at the lowest point where a sample can be taken. The fluid sample this operator is taking will be sent to a lab for testing. The tests can determine contamination levels and content, which can give some clues to the causes of any contamination. When appropriate, the valve can be opened to remove a portion of the fluid from the reservoir to help remove solid contaminants that have settled to the bottom. This reservoir also contains a sight glass. The operator can tell something about the condition of the fluid and its level by looking at it through the sight glass. For example, normal fluid appears clear, but if the fluid appears milky or foamy, it's probably contaminated with water and needs to be treated or replaced. In the example we just saw, the fluid level could be checked through a sight glass, but in some cases a dipstick may be used. If fluid has to be added to the reservoir, the operator has to make sure he uses hydraulic fluids that aren't the proper viscosity or without the proper additives can cause overheating or damage system parts. To reduce the chances of fluid contamination, only a clean container or hose should be used to transfer the fluid from storage to the reservoir. Before hydraulic fluid is added to a reservoir, the area around the filler hole also should be cleaned to avoid getting dirt or other contaminants in the fluid. Some filler holes, like this one, may contain a screen to trap contaminants. Maintaining the proper temperature of the fluid in the reservoir is also important for effective system operation. In this example, the operator checks the fluid temperature on a thermometer within the sight glass. Significant changes in fluid temperature can affect the viscosity of the fluid. Viscosity can be thought of as the measure of how thin or thick a fluid is. Improper fluid viscosity can result in problems such as sluggish actuator operation and inadequate lubrication of moving parts in a hydraulic system. To help maintain the proper temperature of the fluid, and therefore its viscosity, auxiliary devices such as this cooler are sometimes used. Basically, it's a shell and tube heat exchanger like the one in this illustration. In the exchanger, hydraulic fluid passes through the tubes and cooling water passes through the shell. The water carries away the heat from the hydraulic fluid, thereby cooling it. In very cold temperatures, the heat exchanger can also be used as a heater by circulating hot water rather than cold water through the shell. Here, the operator checks the heat exchanger for leaks and proper operation. Another component to check on a hydraulic system is the filter or strainer. Filters or strainers have to be checked to see if there are buildups of dirt and other contaminants which can restrict the flow of fluid. Some filters and strainers can be cleaned, while others use replaceable cartridges. In some cases, they're replaced on a scheduled basis. This filter has an indicator that shows an operator when it needs replacing. The operator in this example also checks a pressure gauge that indicates the system operating pressure. Significant changes in pressure can cause problems. For instance, too high a pressure could blow seals in an actuator and cause an internal leak, resulting in erratic operation. One more thing an operator should check on a system is the actuator. In this example, he looks it over for signs of leaks and to make sure it's operating smoothly. Jerky actuator movement can be the result of deposits of dirt inside the actuator. If hydraulic motors are used in a system, an operator should check them to make sure they rotate smoothly. Another auxiliary device that's sometimes used in hydraulic systems and has to be checked periodically is an accumulator. These accumulators provide a means of storing hydraulic fluid under pressure so that it can be used if the system demand exceeds pump supply or for reserve capacity to the actuator if the pump fails. Now, this is a cutaway of a small accumulator used on a very low capacity system. It contains a bladder, which is normally pre-charged with pressurized gas. Fluid can be stored in this area under the bladder and is discharged here. When additional fluid is needed in the system, the gas pushes against the bladder and forces the fluid into the system. To work properly and avoid damage, these accumulators, like the one we just saw, have to be properly charged with gas. Operators should follow their procedures for the method and frequency of checking the gas pressure on this type of accumulator. The checks we've talked about aren't the only ones you might have to make on the hydraulic systems in your facility. You can refer to your operating procedures or supervisor to find out exactly what your responsibilities are. As we've pointed out, the care and condition of a system's hydraulic fluid is critical to proper system operation, and you're responsible for keeping the fluid up to standards, as well as keeping other system components working properly. The information we've covered in this program should help you carry out those responsibilities.